I have no idea what's wrong with my camera, but we'll worry about that some other time. You have to get by without being able to see me, but you can at least hear me. So here we go. Uh, so once again, we're going to start talking about Ingenuity, the Mars helicopter. And the big news is that it had its first one-way flight, which remember when we were talking about it last week, after it had done the fourth flight, I said it would do one more, and in that flight it would take off and then not land at the same place, but go someplace else different. And that in fact did happen, and it happened back on May 7th. So on the fifth flight, it took off from the same place, which is they named Wright Brothers Field, and it flew 424 feet south. And once it got there, it did something it had not done before. Remember the first flight, it went up about 10 feet high, and then it started going up about 15 feet high. And that's the maximum altitude for its first four flights. On this flight, once it had gotten as far downrange as it was going, it went up to a height of 33 feet. And it took about a lot of pictures up there of the surface. And then it landed at that new location. So that was the fifth flight. And in the original mission, that was it. There's supposed to be 5 flights, and that would be the end of it. But as I said last week, they made the decision that they're going to continue using the helicopter basically as a scout device for the rover. And so the next flight it makes will be when the rover needs some help in figuring out either something it wants to look at or a good route to something it wants to look at. So when I talked about earlier about the helicopter's mission, you know, I said that there was a lot of pressure from the planetary scientists, the people, the geologists basically, who really do run the mission science team, because they wanted to get up to that area of the crater rim where the river delta was and start exploring that. But things have changed a bit, and part of the reason they've changed is that while these helicopter tests have been going on, they have been using the rover cameras to examine the rocks around the area where the rover currently is, and they found out a lot of these rocks are quite interesting. And so they decided that before they go up to the river delta, they want to check out some more of these rocks in the immediate area where the rover landed. Now, you remember that it landed in this crater, which is an impact crater caused by a meteor striking Mars a long time ago, billions of years ago, probably. But that in addition to being an impact crater, that site is also a lake bed, because once the impact crater was there, then a river started draining into the crater and formed a lake. So the situation we have is that when they look around at those rocks, they see two kinds of rocks. They see what we call igneous rock, which is rock, basically it's solidified volcano lava. And that's what was the surface of the crater was originally. And they also see what we call sedimentary rock, which is rock that occurs in a body of water. As the water flows through, sediment and the water settles to the bottom and eventually solidifies and forms rocks. And so both of those types of rocks are present here. The igneous rock is left over when that meteor struck of the surface of Mars and formed the crater. It broke up the lava surface, and a bunch of stuff flew up in the air and then dropped back down to the surface again. And that put a lot of igneous rock down on the surface. And then the river flows in, creates a lake. Over millions of years, sedimentary rocks form in the same area. Now, the problem is that you can't necessarily tell just by looking at a rock which kind it is. Is it igneous or is it sedimentary? So when that happens here on Earth, the geologist knows what to do. He's got a tool called a rock hammer. And so he simply pulls out his rock hammer and he whacks the rock, breaks it open. And by examining the interior, he can decide if he's looking at a sedimentary rock or an igneous rock. Well, we don't have a geologist with a rock hammer up there, but the rover, it turns out, has a tool that's also useful. On the robot arm, it has a tool called an abrader, which is basically a grinding wheel. And so they can lower the robot arm and grind away through the surface of the rock. And then by using their spectroscopic devices, they can examine the rock and deduce whether it's igneous or sedimentary. And they're very interested in doing that because the igneous rocks are most likely much, much older than the sedimentary rocks. And so if we're thinking in terms of being able to find fossils, you don't know whether you would find fossils from billions of years ago or only maybe millions of years ago. And so you would need to look at both types of rocks to see what you would find. And so basically what we're getting around to saying here is that these planetary scientists have suddenly got a great interest in investigating the rocks in the area they're in. And so they want to do that for a while. And the helicopter is kind of the ideal device to help them because it can fly along and take pictures of the rocks that are on the surface. And so they can look at those pictures and decide, what are the most interesting looking rocks they want to check out. And also then it can provide them, with information about the best way to get there. Because they can, if they spot an interesting rock, then they can look and see, okay, on the way over there, are we going to drive into a big hole, or is there a hill we have to get over, or whatever? And so they think that the helicopter will really be valuable for this current work. And so basically what's happening is that the rover's getting back to the mission that it's wanted to go on all the time, but it's going to take it in a slightly different way. And it's going to take it by sending the helicopter out to look and find interesting rocks, and then it's going to go look at them. And so at some point, the helicopter is not really designed to, like the rover is. It's not designed to last for years. So it may fail at some point, but in the meantime, it certainly will help them out. Now we've got a couple of videos to look at. This first one is actually a repeat of the fourth flight. But what is different about it is that they've also released the audio that was taken along with that video, which they didn't release immediately. And when we play this, you're actually going to be able to hear the helicopter blades as the helicopter flies along. Now, the reason it wasn't released immediately is that it's not a very loud sound. We said when we talked about that possibility that it might be impossible to pick up the sound of the helicopter. But it turned out that they actually had recorded that sound. It was very, very low. And so what they did is to enhance the helicopter sound. So when you play this, you're going to hear a very low rumbling sound, and that's the wind. But then if you listen, you'll hear another sound. And I think you'll recognize it. Everybody, I think, has heard a helicopter fly over. And you'll recognize it, that we're actually hearing helicopter blades. So let's get this thing going. Turn this. Now you hear the low rung in the background. I hope you can hear the helicopter blades turning as well. And here comes the helicopter. That little chop, chop, chop sound is the helicopter blades. And in a minute, we're going to see it coming back. Well, I guess we're not going to see it coming back. But we did get to hear the sound, so glad of that. Okay, this is just a still picture of the rocks right around where the rover is now. And I'm certainly not, oops, go back one, no, back. I'm not enough of a geologist to tell you if those are igneous or sedimentary rock, but they're finding that out by using the robotic arm. So that's the kind of rock that's really gotten their interest. Okay, now we're now going to see another video. This is the fifth flight video, and in that video, before we start it, because it's hard to spot this thing when the video is going, but you notice just right next to the start button here, there is this little white area. That's what's called the dust devil. If you've ever been in the desert here, you've seen them here. Same deal on Mars. The wind comes along, basically like a little mini tornado on Mars. So let's get this thing going. Okay, so here's the helicopter taking off. So it's going to go to our left, and it's going to fly off screen, but then they're going to switch cameras, and we'll see it picking up from the other camera. And now it's at its landing position, but you see it going up. That's when it went up to 33 feet, took some pictures, and came back down and landed. So this is actually where it lands at a different site. Now, for some reason, they showed that. Well, they want to show you the change in the altitude there, and then here's an enhanced video of the same thing. I can't really tell a difference myself. And I think they just keep doing this. So I'm going to stop this and let's get on to something else. This is a picture taken by the helicopter of the new landing area. And you can sort of see it's interesting. It's a little different from the area where it first took pictures, and that there are not quite as many rocks here. I think what happened here is, since they were sending it out to someplace that hadn't been, they wanted to get as level a spot as possible for it to land in. And you notice on the left here, that's again, the landing gear of the helicopter showing up in the picture. Okay, so that's basically the story on the helicopter. It will fly again when the rover needs it to fly. When a rover needs some directions on where to go or what to look for, then they'll send the helicopter up to do it. Now, we do have a little more news on Mars, and that is some folks just published a paper in which they suggested something that was kind of a surprise. We know that Mars has had volcanic activity in the past. It has some huge volcanic mountains from billions of years ago. But these people think that it actually had volcanic activity quite recently. And the reason they think so is based on this picture that we see here. In the center of the picture, we have got this fissure, which is actually a fracture in the surface. And then over here, we have this little lava deposit. And this kind of situation where you have a big fracture in the crust and then a lava deposit some distance away, that's very familiar to geologists, because they find this kind of situation in terrestrial geology. This is what happens when you have an explosive volcano. So the volcanic eruption actually happened at the fissure here, and it was an explosion, blew lava up in the air, and it fell and landed over here. Now, in terrestrial geology, that kind of thing will happen when you have some kind of underground natural gas deposit that's close to what we call a volcanic hotspot, a place where the liquid magma that's in the Earth's core is near the surface. And then the heat from the magma will cause the gas to explode. And in that explosion, of magma gets thrown up and lands and forms a lava deposit like this. So this is, it's quite similar to things that geologists are familiar with on Earth. The only thing that's not clear is how did the explosion happen? The natural gas deposits that we have here on Earth, we know are a result of plant material and even maybe dead animals that were buried under layers and layers of earth, and eventually the pressure and the heat converted them into liquid petroleum and natural gas. We don't have any real reason to think anything like that would have happened on Mars. There may have been life there. It's kind of unlikely there would have been life to an extent where something like that would have occurred. But these guys suggest another possibility. We know for sure that there is water, frozen water, under the Martian surface. We remember sometime back we discussed a case where we're using radar from the orbiting satellites. They found an underground lake near the poles, and other locations they've been able to spot places where in in the springtime on Mars, water will come up to the surface and run down canyon walls. So the water is frozen in right below the surface, and when the weather warms up, some of it melts and runs out. So their idea is that there may still be hot magma close to the surface on Mars, and if that came into contact with water frozen in the soil, the sudden heating of that water would cause a big steam eruption, which would have the same effect as an explosion, and that would cause something like we see here. So, and then to support their arguments, they pointed out we haven't mentioned it in a while, but you remember the mission before Perseverance was the InSight lander, and it put down its seismometer, which has been taking readings on seismic waves for several years now. And they point out that it picked up a couple of sizable seismic waves that came from the same area where they saw this fissure and lava deposit. And so that presents further evidence that there may still be geological activity. They're saying that if there still is liquid magma close to the surface and it's moving around, then it would generate seismic waves, and that's what they're picking up. Okay, so that brings us to the end of our story on Mars. Does anyone have any questions about it before we go on? Okay, well, let's move on to our next story. And this is another one of my happy coincidence stories of a couple of topics that we've talked about before coming together. The headline here says, "Machine Learning Accelerates Cosmic Simulations." In the past, we mentioned several times that one of the ways that astronomers try to understand the structure of galaxies and clusters of galaxies, and basically the structure of the universe, is by doing computer simulations. So what they do is they will do a computer simulation of galaxy formation, for example, and they'll run their simulation, and eventually it'll result in producing an image. And they will then, we have lots, thanks to the Hubble Space Telescope and other telescopes, we have lots of galaxy images. So they'll try to match up their simulated image with an actual galaxy image. And then, they don't expect it to be identical, but if they can find an actual galaxy image that looks something like their simulation, then they think they've done a good job with the simulation. And that there might be information to be gotten in that way. Well, how exactly do they do these simulations? Basically, what they do is they use numerical techniques that will allow them to solve the gravitational equations, and depending on the situation, they may simply be using Newton's law, or they may be using the equations of general relativity. But both of them, in that kind of situation, you have to use numerical techniques, because given the amount of stuff that makes up a galaxy, it's impossible to do a purely mathematical solution. You got to do a numerical one. So what they do is they come up with certain assumptions for how a galaxy might form, and they say we get a gas cloud of a certain density, and get subjected to certain kinds of stresses and so on. And they take those assumptions and then they start using their numerical techniques to try to produce a galaxy image of what would be the result of that. And this kind of thing can be fairly successful, but it also requires just a huge amount of computer power, and it takes a long time. And typically, we're not talking, days or even weeks. We're talking months. And because of that, this is kind of a tricky business. If you make an incorrect assumption and you produce your numerical simulation and you run it for 6 months and you come out with, some kind of image, and then you start comparing that to our known galaxy images and it doesn't look like anything, then it's kind of like, oops, well, we just lost a lot of valuable computer time there. So it would be nice to have a more effective way that didn't use as much computer power, that would get us the same kind of results that we can get now when things go well. Well, it turns out that the process I've described that takes months and months takes that long because what they want to produce is a really high resolution image. If you're willing to settle for a cruder image, then it doesn't take so long. And so, and let's just skip up here and look at our illustration here, and then we will see what we're talking about. On the left, we have a low resolution image, and this might take maybe a couple of weeks. And then we have a high resolution image that might take a couple of months, and then a super high resolution image that might take 6, 8, 9 months, even a year. So somebody got the bright idea of let's run when we run simulations, let's take early on, let's take a low resolution image and then let the simulation run for as long as we want it to go. And if it comes up with a good high resolution image in the end, then we can say, well, this low resolution image was something along the pathway to producing the high resolution image. So we can say we can associate the low resolution image with the high resolution image. Okay, so now let's go back and remember a little bit about what we learned about artificial intelligence. One of the things you can do with artificial intelligence is, if you have two different collections of things that are associated in some way, and you have lots of examples of what these things are, you can take your artificial intelligence program and you do what's called training with it, which is you feed it a bunch of examples of one of the kinds of things in the association and tell it what it's associated with. And after it's seen enough of those things, it will be able to modify itself in such a way that it can successfully guess. So to give a much more concrete example, let's suppose that we have a bunch of pictures of different kinds of animals: dogs, cats, cows, sheep, so on. And we feed many examples of each type of animal to our artificial intelligence image recognition program, along with, okay, this is a picture of a cat. This is a picture of a cow. This is a picture of a dog. And we give it lots and lots and lots of examples of each. And the program will modify itself so that after a while, we can give it an image and say, all right, what is it? And it'll say it's a cat. And it'll probably be right. So what the astronomers did is say, okay, here is a lot of low resolution images. Here are the high resolution images that we got by continuing the computer simulation for many, many months. And so the artificial intelligence program learns to associate the low resolution image with the high resolution image. And so then they can start a new simulation, let it run for say 2 weeks, produce a low resolution image, and give that to the artificial intelligence program and say, what do you think the high resolution image will look like? And it will produce a high resolution image. And it might take it might take more than a day, it might take a week even to do that. But basically what you've got is you've got a high resolution image in using say 3 weeks of computer time instead of 9 months or a year or something like that. Well, immediate question is, but how would you know if it was if what you got is really something that's correct? Well, you still have the same test that we had before. We'd compare it to known images of galaxies. And if it looks like something, then okay, it's probably correct. And if it doesn't, then there's probably something wrong. But the main advantage here is now you get your answer in maybe 2 or 3 weeks instead of 8 months, 9 months, a year, something like that. Okay, anybody have a question about that? Okay, so we have, oh, and here's just a little diagram that shows the process it goes through in looking at the images and training itself to finally be able to produce an answer. Okay, so our last story is a story about quantum mechanics. And this interested me because quantum mechanics always fascinates me, but it's also interesting for another reason that we'll get to. The headline says, physics experiment demonstrates quantum entanglement with tiny drums. And the tiny drums part was what kind of caught me. I mean, how do they make tiny drums? What do they mean by that? And so on. We need to go back and remember what we're talking about when we talk about what we call quantum entanglement. It's one of the very weird quantum properties that physicists deal with. And actually, Albert Einstein was the person who really brought it into prominence. But he did it in a very contrary way. We remember we talked about quantum mechanics, that though Albert Einstein can truly be considered one of the founders of quantum mechanics, because he all the way back in 1905, he explained the photoelectric effect by using the fact that the energy was quantized. But then when quantum mechanics started dealing with probabilities and things we call quantum jumps and so on, he thought they'd gotten on the wrong track, and that there had to be something else about quantum mechanics. It couldn't be that it involved probability in such an intrinsic way. He just was not happy with that. And so in order to try to convince other people that quantum mechanics, well, people often say, well, Einstein said quantum mechanics was wrong. Well, that's silly. He wouldn't have said it was wrong because he helped start it. What he said about it was it's incomplete, that we don't really understand everything about it. And in a certain sense, that's obviously true, but it's not, we don't really misunderstand it as badly as he thought we did. And we'll try to explain that as we go along. But what he proposed was an experiment that could be done. And the purpose of his experiment was to show that we don't properly understand quantum mechanics. And the experiment he proposed was this, that you could somehow in a laboratory, you could produce a pair of particles, an electron and its antiparticle, a positron, and have them shoot off in opposite directions. Well, one of the things we learned when we studied quantum mechanics is that electrons and positrons have a quantum mechanical property called spin. And the spin can take one of two values. It's either up or down. And since in the experiment that he described, we started with a photon, which has no spin, and we produce the electron and positron, it has to be true that one of them has spin up and the other has spin down, which basically nets out to zero spin, which is what we started with. So Einstein said, well, we let these things fly apart and let them go for a while. And then we measure, say, the spin of the electron. And let's say it turns out to be spin up. Well, instantly, we know that the positron has got to be spin down because they have to have opposite spins. But if they've gone for a while, then the positron, they might be 1,000 light years apart. And there's an intrinsic problem here with the theory of special relativity, which says that nothing can travel faster than light. And somehow we know a property of this positron, which is 1,000 light years away immediately. We don't have to wait 1,000 years for information to reach us to tell us what its spin is. We know it. And he said, this shows that quantum mechanics has to be incomplete. Well, the physicists who believe strongly in quantum mechanics would basically, they were tending to be all followers of another famous physicist named Niels Bohr. And Bohr and his followers said, no, your argument is all wrong. But the problem was that the way we would describe this experiment in 1935, you could not do it. It was just beyond technical possibility to do anything like this. And Einstein knew that, of course. He knew that, you simply, you couldn't do this experiment. His whole idea was he would propose the experiment and say, until you can do this thing and actually measure those spins, here's my argument for why quantum mechanics has to be incomplete. And he really thought it would never be done. But he was incorrect in this. In the late 1970s, some people actually managed to do that experiment. And when they did it, they didn't do it over thousands of light years because that would be impossible. But they actually, it's been done. The original experiment was done where the particles were separated by, a couple hundred feet, but it just keeps getting repeated, and they're able to do it now where they're separated by several hundred miles. And so what they do is they set up detectors and they intercept the two particles and measure their spin. And sure enough, it turns out that those spins are always opposite. And so Einstein's argument fails. It doesn't show that quantum mechanics quantum mechanics might be incomplete, but his argument doesn't show it's incomplete. Well, that property of the spins of the particles having to be always opposite is what we call entanglement. And it's fascinated physicists for a long time. When we're dealing with electrons and positrons, it seems okay, sure, they might be entangled. They're just little tiny things and we'll never see them. But that made other physicists want to try and do entanglement experiments with things you could actually see. And until recently, that had not been done. The best result until very recently was to entangle certain combinations of carbon atoms. You can get carbon atoms to combine in a crystal-like structure that's called a buckyball, and it contains 60 carbon atoms. And people had managed to entangle a couple of buckyballs. So that's a much more substantial thing than an electron and a positron, but still, it's microscopic. We can detect buckyballs, but we can't actually see them. So people really wanted to be able to do an experiment like this with things you could actually see. And now that's been done. At the National Institute of Standards and Technology, the same place where they devised the super good atomic clock we talked about a few weeks ago. They built an apparatus that consisted of a couple of tiny aluminum membranes. So tiny, they're about 10 millionths of a meter long, and they're mounted on a piece of silicon. Now, 10 millionths of a meter is pretty tiny, but if you have good eyes, you can actually see it. So these little membranes, a person with good vision can actually see these things. And they were able to show that they could put them in quantum superposition by cooling down that piece of silicon to almost absolute zero, and then bombarding it with microwave radiation. And that would start each of those little membranes vibrating like a drum head. But they were able to do it in such a way that they could measure the vibrations, and they could see that as one of those little membranes was going up, the other was going down. And so they had exactly opposite velocities. So that's where the entanglement comes in. So there's not really a practical application for this yet, but it does satisfy the desire to try to see quantum mechanics brought more into what we might consider the macroscopic world, the real world that we live in, and that we actually can now see a quantum property occurring in a couple of objects that are really and truly macroscopic. Now, the article I read said that there may be applications of this to quantum computing and this and that, but they didn't give any real description. So I can't really say that this experiment is going to result in any great development in any particular area. But it just fascinated me that we could finally do this in something that we could see. Okay, we have any questions about this one?
Bill,
Yes.
do you have any idea how rapidly these things are vibrating?
Well, it's microwaves,
Okay.
which they're relatively low frequency radio waves. So it would be like off the top of my head, it's certainly a lot less than optical frequencies,
Yeah.
but it's still reasonably fast. It'll be in the order of hundreds of thousands of cycles a second, but not millions.
Okay. Yeah. Okay. I just have a comment about the membranes. You speak of those being 10 millionths of a meter long. I believe that means that they're 10 microns long,
Right. Yes.
which means that they're only a little bit longer, about 1.5 times as long as a red blood cell is wide. So I doubt you'd be able to see it with a naked eye. You could
Yeah.
certainly see it with an optical microscope.
Yeah.
You wouldn't need an electron microscope,
Yeah.
but I doubt you could see it.
Yeah, well, I'm not certain of that. I did kind of wonder about that myself, but the articles definitely, maybe they have a guy who has super good vision who looks at these things. I don't know.
Yeah.
But as you say, certainly with just a standard laboratory microscope, you could see them for sure.
Yeah. Well, I used to use those in hospital labs a lot. And I know what I could not see and what I could see with
Yeah.
these things. And
Yeah.
the regular optical microscopes could multiply things by about 1,000. But and that's fine for red blood cell, but or bacteria. But it wouldn't be too good for this, for visual viewing.
Yeah. Right.
Anyway, yeah.
Okay. Any other questions, comments? Okay, well, I apologize for the technical difficulties. I'm going to have to check out my laptop and see what's going on, because I know my camera worked last week, and I can't think of any reason for it to stop. But at least we found a way to make it work. So, I can't promise you'll be able to see me next week, but you'll definitely be able to see the class. So I hope to see you all back next week. Thanks very much for coming today. And
thank you.
See you later.
Good class. Thank you.
Thank you. Hello. Hello. Not completely. Sure. Yes.